Okay, so today we're taking a look at rational functions. So rational functions are functions of the form y equals f of x over g of x, where f of x and g of x are both polynomial functions. So the top part's going to be polynomial function and the bottom part's going to be a polynomial function. One of the things we need to watch out for is to make sure that the polynomial function at the bottom does not equal 0. Okay, otherwise the function is going to be undefined. So the characteristics of the graph of a rational function can be determined from an equation of the function. So our goal for today's lesson is to look at the equation of a rational function and try and determine what some of the properties of that rational function are. So here is the first characteristic that we need to worry about, the non-permissible value of x. Two possible things can happen when there's a non-permissible value. One of the things that can happen is you can have a vertical asymptote or you can have a hole. Now here are some key points that we need to watch out for when we have either a vertical asymptote or a hole. The vertical asymptote is going to happen when there is one or more non-permissible value. So first of all, we need to have a non-permissible value for there to be a vertical asymptote. It's also going to happen when there are no common factors between the numerator and the denominator. And if the numerator and the denominator do have a common factor x minus a, and the numerator has a greater degree, the denominator has a greater degree of x minus a factor than the numerator, then there will be a vertical asymptote. So for example, on the side here, I'll write it down. If you had a function of the form x minus 3 squared at the top and x minus 3 cubed at the bottom, then the x minus 3 factor at the bottom will have a higher degree than the top. If that's the case, then we're going to have a vertical asymptote. Okay, so the bottom one's going to have a higher degree. We're going to have a vertical asymptote. We're going to have a hole on the graph when, again, first of all, is we need to have a non-permissible value. So the first criteria is there need to be one or more non-permissible values. If there's no non-permissible values, then we're not going to have any hole or any asymptote. The second criteria, again, is this time we do need to have a common factor between the top and the bottom. And this time, the power of the common factor x minus a in the numerator needs to be bigger than the one in the denominator. So for example, again, if I have a common factor x minus a, then the power of x minus a at the top needs to be higher than the power of x minus a at the bottom. Now the key idea behind there is if any factor top and bottom crosses off, right? Because when the power up at the top is going to be bigger, what will end up happening is we'll have two factors of x minus a and x minus a, and at the bottom we'll have one factor of x minus a. So one of these factors is going to cross off. So whenever a factor crosses off, that's the main criteria for having a hole. Whichever factor crosses off, at that factor there is a discontinuity that's going to be a hole. In this scenario up here, we're going to have factors cross off. And what's going to happen is these are going to cross off. Let's say there's a hole there. These are going to cross off. Let's say there's a hole there. Still one factor is going to be remaining at the bottom. So now we have a criteria where there's a hole at 3, but because that part's left at the bottom, there's also an asymptote at x equals 3. So when you draw it out, the asymptote is going to overlap with the hole, which means the asymptote is going to be the one that we count, because it's going to be more points of discontinuity along that asymptote, rather than just the one point of discontinuity on that hole. Right? So that's why we're going to be left with the denominator, and that's going to give us an asymptote. Asymptote trumps hole if they're in the same location. So the asymptote's going to win over, and that's what's going to be the case. Okay, those are two main criteria in working with the vertical asymptotes and the holes. Let's look at some examples here. Okay, here are our first examples. I've already factored these out for you. So let's take a look at the first scenario. If I look at the first scenario, I have two factors, x plus 3 at the bottom, x minus 3, and x plus 1 at the bottom. You'll notice that I have no common factors here. No common factors. So I know chances are I don't have a hole in this particular function. I do have two non-permissible values. My non-permissible values are going to happen at non-permissible at x equals 3 and x equals -1. Those are the non-permissible values. Which means I'm going to have a vertical asymptote at x equals 3 and x equals -1. Because there's no common factors, I still have two factors at the bottom that are non-permissible values. Both those non-permissible values are going to be vertical asymptotes. We can also talk simultaneously about horizontal asymptotes here. We discussed a little bit yesterday the scenario where we have a horizontal asymptote. Do you remember what that was? When the degree of the bottom is going to be greater than the degree of the top, we're going to have a horizontal asymptote. Right? So in this particular case, if you look at the bottom, bottom is degree 2. The top is degree 1. So the bottom is going to be 1 degree higher than the top. As a result, we're going to have a horizontal asymptote. And whenever that's the case, the horizontal asymptote is going to happen at y equals 0. So horizontal asymptote at y equals 0. And the reasoning for that is horizontal asymptote since degree of denominator is greater than degree of numerator. I wish I'd given you more space to work with here. Alright, what I need you to do now is I need you to go ahead and try the other examples. Just look at the similar scenarios and try and predict without graphing what type of behavior we're going to have. And then we'll compare answers in a few minutes here. So I want to give you some time to go ahead and try the rest of the examples using the same concepts, and then we'll compare our work. Okay, go ahead, give that a try. So let's see what you guys came up with here. So one of the things that I want to point out is when I'm referring to common factors, I'm referring to common factors between the numerator and the denominator. Right? So common factors between numerator and denominator, not between the denominator amongst themselves or the numerator amongst themselves. So between the two of them. So for this next example here, what do we have for our non-permissible values? Yeah, x equals 3 and x equals -1. Okay, that's the first thing that I need to identify, the non-permissible values. The next thing I look to see if there's any common factors. Do I have any common factors this time? Yeah, I have x minus 3 is a common factor. So as a result, if I simplify this expression, what I'm going to end up with is the following. X plus 3 left at the top. At the bottom, I'm going to have a factor of x minus 3 and x plus 1. So even though x plus 3 was a common factor, the degree of that common factor at the bottom is greater than the degree of that common factor at the top. As a result, even when you cross them off, x minus 3 is going to remain at the bottom, which means you're going to have a vertical asymptote. So as a result, we're going to have a vertical asymptote at x equals 3, and x equals -1 is also going to have a vertical asymptote. Right? So as a result, we're going to get two vertical asymptotes, x equals 3 and x equals -1, even though we had a common factor this time. What about horizontal asymptotes? Do we have any horizontal asymptotes this time? For horizontal asymptotes, you're comparing the degree of the top to the degree of the bottom. What do we know about the degree of the top? Degree is not 1, 2. It's a linear multiplied by a linear, which is a quadratic. And what about degree of the bottom? Degree 3. So since degree of the bottom is 1 more than the degree of the top, then we know that we're going to have a horizontal asymptote at y equals 0. So far so good? Okay, let's look at the other examples now. So in this particular example, again, we first identify, do we have any non-permissible values? For the non-permissible values, you always look at the original function before you simplify it. So looking at the original function, do we have any non-permissible values? Yes, we have one at x equals 3. Once you identify the non-permissible value, our next step is to classify it, whether it's a whole or an asymptote. To do that, I look at the expression and try and simplify it. This time, I do have a common factor again, and the common factor crosses off. So common factor x minus 3. Once that common factor crosses off, I look at the resulting function. I just get x minus 3 and x plus 1 left over. The fact that we have a common factor tells us that there's going to be a whole at x equals 3. I look at the resulting function. There is no more non-permissible values, which means I'm not going to have any more wholes or vertical asymptotes here. And the fact that the degree of the common factor at the top was bigger than the degree at the bottom, I still have a whole, not a vertical asymptote. Alright, one other thing that I need now. Once I know that the whole happens at x equals 3, I also want to identify the coordinate of that whole. So to do that, I know that the x value of that whole is going to be 3. I also want to figure out the y value. Now if I plug in x equals 3 into the original function, I'm going to get something over undefined. So I'm not going to do that. I'm going to instead plug it into the resulting function once I've simplified it. So once I've simplified that expression, I'll take x equals 3, I'll plug it in there. I'll get 3 minus 3 is multiplied by 3 plus 1, which is basically 0 times 4, which gives me 0. Right? It's no longer undefined value. So I can plug in the x coordinate of that whole into the resulting simplified function and get the y coordinate for that. And the y coordinate corresponding with that is going to be 0. So the whole is going to have a location at 3, 0. That's going to be the location of the whole. Any horizontal asymptotes this time? And the answer is no. The answer is no because the degree of the top is bigger than the degree of the bottom. And whenever that happens, we no longer have any horizontal asymptotes. If you try to visualize what this function is going to look like, if you were going to graph this, what you would have is you would have this resulting function being graphed. The resulting function is going to be a parabola. Right? So you're going to end up with a parabola, and somewhere in that parabola is going to be a hole located at 3, 0. So you're going to end up with a parabola with a hole in it. That's what this function is going to look like. Let's look at the next example. X squared over 9 minus x squared. This one needs to be factored, so I'm going to go ahead and do that first before I can compare them or make any statement. So the factors are 3 minus x and 3 plus x using difference of squares. Once I've done that, I can identify the non-permissible value. It's non-permissible at x equals plus or minus 3. Okay, both positive 3 and negative 3 are non-permissible values. No common factor, so I know there's not going to be any holes, which means I have two vertical asymptotes at plus or minus 3. So as a result, I have vertical asymptotes at x equals plus or minus 3. The next part is I check for horizontal asymptotes. Do I have horizontal asymptotes this time? And the answer is going to be yes. Horizontal asymptotes happen in two scenarios. Either the degree of top and bottom are equal, or the degree of the bottom is greater than the top. In this case, you'll realize that the degree of top and bottom is equal. Now, the difference here is that when the degree of the bottom is bigger than the degree of the top, the horizontal asymptote happens at y equals 0. But when they're equal, then we no longer look at y equals 0. What we have to do at that point in time is we look at their leading coefficients. So here, the horizontal asymptote is going to happen at the leading coefficients divided by each other, which means the leading coefficient at the top here is 1. The leading coefficient at the bottom is negative 1. So 1 over a negative 1 gives me negative 1. Which means I'm going to have a horizontal asymptote at y equals negative 1. That's going to be the location of the horizontal asymptote. The reason why I got 1 and -1 is because I need to look at the leading coefficients of my function, which means the function needs to be rewritten in proper standard form. If I rewrite it in proper standard form, I'll get the following function: y equals x squared over negative x squared plus 9. Then I'm just looking at their leading coefficients. Leading coefficients, the number in front of the highest powered variable. So 1 and 1. 1 divided by -1 is -1. So that's where the horizontal asymptote is going to be. We've covered a lot of different concepts in one go, and I think once we get a bit of practice on there, they're actually not going to be that bad. So let's write down the factors for that. The factored form of that works out to x plus 1 and x minus 2 all over x plus 1. Step 1, identify any non-permissible values. Do we have a non-permissible value this time? Yes, we have one at x equals -1. Before I do any crossing, before I do any reduction, I identify the non-permissible values. Now that I know there's a non-permissible value, it's going to be one of either a whole or an asymptote, not both. It can't be both at the same time. So the next question is, are there any common factors? And the answer is yes, there are common factors. That x plus 1 and the x plus 1 is a common factor, so therefore I know that there's a whole at x equals -1. And more specifically, I can write the coordinate for that. It's going to be -1 comma, what's going to be the y value of that whole? -1, -3. How did you get the -3? Yeah, I looked at the reduced form of that equation. The reduced form of that equation is simply y equals x minus 2. And then when you plug in the -1 in for x, you get y equals -3. So just thinking out loud, what kind of a visual shape would you expect this function to have? What kind of a graph would you get? You're going to get a linear function with a hole in it, right? Because you always graph the resulting function. The resulting function is a linear function, which is a straight line, and it's going to have a hole in it. Now, a little bit of common sense you have to use also. If you have a straight line, chances are your straight line's not going to have an asymptote in it, right? So if you're working with a resulting graph that's a linear function, it can have a hole in it but not an asymptote. So just watch out for that. Next one, again factor it out. X plus 5, x minus 5 all over x plus 5. No, I didn't mention anything about a horizontal asymptote in the previous example. Why not? Why didn't I bother looking for horizontal asymptote? Absolutely, the degree of the top is higher than the degree of the bottom, so I know that there is not going to be a horizontal asymptote there. Also, the fact that it's a linear function having any asymptotes doesn't make any sense to me. That one again, non-permissible. All sorts of random stuff is popping up. Non-permissible at x equals -5. That's the first step. Then I look for common factors. There's a common factor at x plus 5, x plus 5. So that means there's a whole at -5 comma, what's the y coordinate? -10. You're getting good at this. That's awesome. Any horizontal asymptotes? Nope. No vertical asymptotes because the resulting function is linear. One last example from this section here. Again, start off by taking out factors, fully factored form. So fully factored form of that's going to be 2 brackets 2x plus 1 over x minus 2. Again, I have a non-permissible value at x equals 2. Which means a vertical asymptote. Again, it's a vertical asymptote because there's no common factor between top and bottom. At x equals 2. Next question I ask myself is there a possibility of a horizontal asymptote here? And you're nodding your heads, that means yes, there's also a horizontal asymptote. The resulting function is still going to be a linear over linear, right? So we could have a horizontal asymptote. Where is that horizontal asymptote going to be? At y equals 4. Again, the reason why it's y equals 4 is because you look at the leading coefficient. Right? So the leading coefficients there are 4 over 1, which is 4. So that's where your horizontal asymptote is going to be, y equals 4. So we've covered all the key concepts regarding horizontal asymptote, vertical asymptote, and a hole. And we're going to build on these in a few more minutes here in a bit more detail. Let's try another example here. Suppose the graph of a rational function has the shape of a parabola with a hole in it. What is an equation of a possible function, and what are the coordinates of that hole? Open-ended question. I'm giving you the criteria and the description of a function. It's a parabola with a hole in it. You need to work backwards and try and figure out what one possible equation is going to be. Now, because it's an open-ended question, we can have unlimited number of different expressions that will have this sort of a graph. So let's see if you can come up with one possible expression. I'll give you a moment to give this a try, and we'll compare answers. Okay, so because we want to end up with the parabola, we know that our resulting function is going to have to be a quadratic equation, and the whole represents that we're going to have a common factor. So one possible solution we can have is we start off with the fraction. It's going to be easier to identify a whole first, so we can say we have a whole at x plus 1 and x plus 1. That could be our common factor. And then once those common factors cross off, we want to end up with a parabola left over. So if I just make the top equation another quadratic function, could be any quadratic function, that would be one possible solution. So I could add two more factors here, say x plus 3 and x minus 2. And as a result, this resulting function, this cubic over a linear, would give me a parabola with a hole in it. Sounds good? Okay. Next up, we take a look at formally the definition of horizontal and this new idea of oblique asymptotes. So I've already gone over the horizontal asymptotes as we were doing the example. Let me formally summarize that for you now. So the graph of a rational function y equals f of x over g of x, where f of x and g of x have no common factors. We start looking at horizontal asymptotes taking away the common factors. A horizontal asymptote is going to happen at y equals 0 if the degree of the top is less than the degree of the bottom. The horizontal asymptote is going to happen at a over b, where a is the leading coefficient and b is the leading coefficient of the bottom function, if the degrees of f of x and g of x are equal. So we already discussed that. If the top is less degree than the bottom, then it's y equals 0 for your horizontal asymptote. If the top and bottom are same degrees, then you look at the leading coefficients a and b, and their division is going to result in a horizontal asymptote. One final type of an asymptote we have is something called an oblique asymptote. An oblique asymptote is a diagonal line which the function behaves asymptotically around. So for example, if you had a function that's doing something like this, then that function is asymptotic along a diagonal line, this diagonal line. And that diagonal line represents an oblique asymptote. Now what's going to happen is functions will have an oblique asymptote if the degree of the top, f of x, is 1 more than the degree of the bottom, g of x. Right? So whenever the top is going to be 1 more than the bottom, we do have a possibility of an oblique asymptote. We're going to look at their degrees after we have reduced them, after we've taken out any of the holes, because we're looking at the form which has no common factors. We're looking at the reduced form now to figure out if there's an oblique asymptote or not. So let's make sense of this using some examples. So consider the following functions. First, we're going to use the equations to predict what kind of asymptotes they have, and then we're going to identify those asymptotes. And lastly, we're going to use a graphing calculator to verify that our graph actually makes sense. So let's look at our work. Our first step is factor. Let's go ahead and factor that. Factor it out. You get x over 3 minus x, 3 plus x. Next step, identify the non-permissible values. So in this case, we have two possible non-permissible values. It is non-permissible at x equals plus or minus 3. Once we've got those two items figured out, we look to see if there is a common factor. And the reason why we're checking that is so we can identify whole or vertical asymptote. Third step is identify non-permissible values as either whole or vertical asymptote. Again, we're going to do that by looking for common factors. In this particular example, we do not have any common factors, so what can we say about the non-permissible values? They're going to be vertical asymptotes, right? And then lastly, I'm going to check for oblique or horizontal asymptotes. Now, one of the things I want to point out to you is, notice I mentioned oblique or horizontal asymptote. The criteria for oblique asymptote is that the top part f of x has to be one more than the bottom part. Top is one more than the bottom. The criteria for horizontal is top and bottom are equal, or top is less than the bottom. So can we have both horizontal and oblique at the same time? No, because they are sort of dependent, right? If the top and bottom are same, horizontal. Top is less than the bottom, horizontal. Top is bigger than the bottom, then that goes against the criteria for horizontal, so we're going to have an oblique asymptote there. So you're either going to have an oblique or you're going to have a horizontal, not both. Good? Okay, going back to this part over here. We look at this function, we have the bottom polynomial is a higher degree than the top polynomial, so as a result we say degree of denominator is greater than degree of numerator, and that means therefore we have a horizontal asymptote at y equals 0. Horizontal asymptote at y equals 0. Let's try one more example here. Actually, I'll leave that one for you to try. Let's jump to part C here. Okay, again we're going to look at our steps. Our step 1 says we're going to factor that. So step 1 is factor, so let's factor that. X squared plus 6x minus 7. So the two factors I'm going to get, two numbers that multiply to give me negative 7, add to give me 6. 7 and negative 1. 7x minus 1. At the bottom I have x plus 2. First step done. Next step, identify non-permissible values. So I'm going to say non-permissible at x equals negative 2. Third step, look for common factors. Do we have any common factors? Nope. Which means our non-permissible value represents a vertical asymptote at x equals negative 2. I've got that taken care of. Because there's no common factors, is not going to be a reduced form of that function. Last part, I look for horizontal or oblique asymptotes. Again, I compare the degree of the numerator and the bottom. You'll notice the degree of the numerator is bigger than the degree of the bottom by 1. Right? So that means we're going to have an oblique asymptote this time. Now the new part here, how are we going to find that oblique asymptote? This is where you have to use information that you learned in the previous chapter. So let me first write that part down here. Since degree of numerator is 1 greater than degree of denominator, I'm going to abbreviate with denom. There is an oblique asymptote. Okay, now the fun part about identifying the oblique asymptote. How do we identify the oblique asymptote? Well, to identify the oblique asymptote, we have to divide the two expressions. So on the side here, I'm going to do that. The work for oblique asymptote. We're going to go ahead and divide the two expressions and then write it in division statement form. Divide the two polynomials and write a division statement. Okay, so I'm going to use synthetic division to do that division there. So I will set it up. The leading coefficient is 1, so I have 1, 6, and -7. I'm dividing it by -2. So as a result, using synthetic division, I'm going to get 1, -2, 4, -8, -15. And if I write it in a division statement form, there's two forms of division statements, right? One of the ones we looked at was P equals dq plus r, and the other one we looked at was P divided by d equals q plus r divided by d. If I divide everything by d, I'm going to get that form. So polynomial divided by the divisor equals quotient plus remainder over the divider. Because this expression is in the form of that statement right here, polynomial divided by the divisor, I'm actually going to write it in this form right here. Quotient plus remainder over the divisor. So what my division statement is going to look like is this. I'll leave the left hand side as it is, and I'll get the following statement. Polynomial divided by the divisor equals. The quotient is by itself, so the quotient is going to be this part right here. So x plus 4, and then minus remainder divided by the divisor, so 15 over an x plus 2. Now this information is going to be used to figure out the equation of an oblique asymptote. The easy solution is this part right here is the oblique asymptote. The explanation behind that is why that's an oblique asymptote is because an oblique asymptote is going to happen when your x values get really, really big. They reach infinity. That's when your values are going to reach the asymptote. So if we think about this expression, if x becomes really, really big, then in this expression over here, what's going to happen is, as absolute value of x, which means both positive direction and negative direction, as positive value of x approaches infinity, it gets really, really close to a big number, then your graph is going to approach the asymptote. Then we're going to get the asymptotic value. What's going to happen to this function is, as x becomes a really, really big value, that expression 15 over x plus 2, it's going to equal 0. Because when x becomes a really big number, 15 divided by a really big number is going to equal 0, or 15 divided by a really big negative number is also going to equal 0. You're going to end up getting closer and closer to 0, which means this portion over here is going to become 0, and what you're going to be left with is this x plus 4 statement. And that x plus 4 statement tells you the value of your oblique asymptote. Right? That's the justification behind why x plus 4 is the oblique asymptote. So as a result, we say we have an oblique asymptote at y equals x plus 4. Now, of course, when you're writing this statement every single time, you don't need to give me that explanation every single time. You just need to recognize that this portion over here is going to be the oblique asymptote. So now you know how to figure out an oblique asymptote. So as a result, in this particular function, when you graph it, you're going to have a vertical asymptote at x equals -2 and oblique asymptote at y equals x plus 4. Those are the two statements. What you can do now is try the other examples we didn't do. So part B and part D, again, just identify what sort of behavior they're going to have. Once you've had a chance to try those two examples, these are the answers you should end up with. For part B, we end up with a vertical asymptote at x equals 3 and an oblique asymptote at y equals -x minus 3. Also, for part D, we end up with the following solution. We end up with a vertical asymptote at x equals -7 and x equals 1, as well as a horizontal asymptote at y equals 0. Okay, let's get a little bit more practice on this as well. There's more examples on the next page. So example number 4 will give you a bit more practice on this concept. So take a few minutes, give that a try, and I'll go over the answers with you once you've had a chance to give it a try. Okay, so let's discuss example 4a. Our first step in this example is to go ahead and factor the polynomial. Once we factor the top, we realize that there is no common factor, but we do have a non-permissible value at x equals -1. We then state that the non-permissible value at x equals -1 is a vertical asymptote because there is no common factor top and bottom. Once we figured that out, we also realize that the degree of the numerator is bigger than the degree of the denominator over there. As a result, we have an oblique asymptote. So then we go about finding the oblique asymptote. To do that, I set up my synthetic division, and what I end up getting is the following expression. And in this expression, I know that the first part over here represents the equation of the oblique asymptote. So therefore, I have an oblique asymptote at y equals x. And lastly, the domain of this function is all real numbers except x cannot equal -1 because that's where the vertical asymptote is. So when all is said and done, this particular graph will have these two aspects, a vertical asymptote at x equals -1 and an oblique asymptote at the line y equals x. Let's look at the next example, 4b. For this particular example, again, you have to first start off by factoring. When you factor it out, originally it'll appear that there are no common factors, but once you simplify it even further, you'll realize that x minus 1 is a common factor both the top and the bottom. As a result, I state that x minus 1 is a common factor, which further means that there is a hole at x equals 1, and the coordinate of that hole is going to be 1, 0.5. The remaining factor that's left at the bottom will give us a vertical asymptote at x equals -1. Once I've got that figured out, I'll realize that the degree of the numerator is bigger, or actually equal to, the degree of the denominator. As a result, I know there's also a horizontal asymptote, and the horizontal asymptote is going to happen at the division of the leading coefficient. So 1 divided by -1, which is going to give me a -1. So I have a horizontal asymptote at y equals -1. Lastly, the domain. This particular function is going to have a domain of all real numbers except at the non-permissible values, which is x equals plus or minus 1. So finally, this graph is going to have a vertical asymptote at x equals -1, a horizontal asymptote at y equals 1, a hole at 1 and 0.5, and those are some of the properties of this function. Okay, as part of our last example in the notes today, we're going to learn how to use graphing technology to solve the following rational equations and give the solution to the nearest tenth, one decimal place. So what we need to do here is very similar to what we've been doing with other functions. It's just a matter of us taking this expression and plugging it into a graphing calculator. So to do that, what I have done is I have brought everything over to one side of the equation. I brought the entire expression over to the left hand side there, and then it equals 0. So what I can do next is I can take this expression, plug it into my graphing calculator, and look for zeros. So my two steps are bring all terms to one side and then look for the zeros. You can also graph the left hand side and the right hand side separately and look for the intersection points. That's an alternate method as well. So for this particular example, let's give it a try. You can go ahead and plug it into your graphing calculator. When you plug that expression into your graphing calculator, this is what it's going to look like. X plus 6 minus x minus 1 over x plus 1. You will then go ahead and graph that, and when you graph that, you're going to get a graph that looks like this. Now this particular graph is going to have two zeros. The zeros are going to happen right here and right here. I can zoom in a little bit if I wanted to. I could do a zoom box and sort of try and zoom into that area so I can see what those zeros are. When I zoom into that area, you'll notice that there's a 0 over here, there's a 0 over here. If I want to trace those zeros, I just go second trace 0. I go to the left of that 0, press enter. I go to the right of that 0, press enter, and then press enter for the third time, and I'll get a 0 of negative 4.41 when y is 0. So that's one of the points I have over here, negative 4.41. Similarly, for the second one, I can do the exact same thing. I can actually jump faster if I go second arrow. It'll make it jump a bit faster here. I just need to be on the left hand side of that 0. Press enter, go to the right side of it, press enter, and then press enter for the third time, and you're going to get your second 0, which is negative 1.587, and then that's going to be our second 0. Sometimes, I'll go back to zoom 6, which is a standard graph. Sometimes the graph looks like there's an asymptote, but it's not an asymptote, it's a graph, so you really have to zoom in and try and check to see if there's a 0 there or not. That's how you find zeros. These are the two zeros that we're going to have. I know we said we're going to round to the nearest 10, so let me go ahead and do that. So when we round to the nearest 10, this is going to become negative 4.4 and negative 1.6. Right, similarly try the next example, and the answer you will end up getting for that particular example is the graph will look like that, and your 0 will end up being 1.8. You can confirm that in your graphing calculator, and that's the answer you should be getting. Thank you for watching. Good luck with your homework.